Welcome back. This is CS 480/680, Introduction to Machine Learning, as taught at the University of Waterloo in fall 2024. This is lecture 13, and today we're going to be getting into deep learning and talking about multi-layer perceptrons specifically. Okay, so far in the course and this lecture series, we've encountered models that would allow us to deal with problems that have kind of ranged in difficulty. And so we started off by assuming that the features of the data itself, so x1 through xd, so we started off by assuming that those features themselves, that was enough for us to learn a classifier. Um, and so we the perceptron algorithm that could handle the case of linearly separable data. So the Setosa class in the iris data set was linearly separable from the other two classes in that data set, versicolor and virginica. And that meant that we could draw a decision boundary that would perfectly separate those two classes. And so this decision boundary, that was an affine combination of the input features. So all we had to do was learn the weights of those respective to apply to those respective input features, and then add a bias, and that would determine and set our decision boundary. And then in support vector machines, we learned how to handle, I guess, the optimal decision boundary, the best that we could do in the case where the classes overlapped, as was the case between the other two classes in the iris data set, versicolor and virginica. I guess specifically in that case, the decision boundary ended up reducing to a linear combination of just a few training examples, and we called those support vectors. And then we started looking at harder problems. We encountered some data sets where a linear decision boundary just really was not going to cut it. It was insufficient to capture essential features in the data set. So for example, we encountered a data set where one class was nested or partially enveloped within another. And we used this prior knowledge of the problem by going and physically looking at the data. We used that to design an appropriate way to map features for the problem at hand. And so what that looked like in our architecture is that we had our original input features, and then we passed all of those into some black box to generate some new set of features, and then we learned how to weight those features to specify our classifier. And so those feature maps, what could go on inside this box, that fell under a very general family of functions that mapped from R to the D to some other space R to the N. So there's tons of functions that could fall under that umbrella. We were most interested in nonlinear functions. And very often we wanted to map to some higher dimensional space. So typically nonlinear, typically higher dimensional space. So M was greater than D. Coming back to this example, we recognized that what we really needed was some kind of elliptical decision boundary. And so there, in this case, we used the quadratic feature map, which gave us interaction terms between x1 and x2, as well as squared terms, so x2 squared and x1 squared. And so we use that feature map to project the input data into a higher dimensional space. Specifically, in this case, we went from a feature space of 2 to 6 unique features and provided by the quadratic feature map. And then in that higher dimensional feature space, it turns out that these two classes were linearly separable. I'm not showing that linear separability. It's hard to visualize a six-dimensional feature space, um, but that was the trick we were using. And so, yeah, in that six-dimensional feature space, the classes were linearly separable. But then when we observed the behavior of the classifier that we learned, when we went back to the original feature space, the original input space to see what that classifier was doing, it made the decision boundary clearly nonlinear. And then, yeah, using that together with support vector machines, we were able to separate the two classes. So that approach got us pretty far. We encountered the radial basis function kernel, polynomial kernels, um, really powerful methods. But a limitation of that approach is that it demands that we know something about the data and the problem in order to bring our prior knowledge to bear on the task. We have to have prior knowledge in order to apply it. And so, yeah, let's consider another problem that's of interest to machine learning, that of handwritten recognition of handwritten digits. So uh, these images here are examples from the MNIST handwritten digit data set. And so there's yeah, digits 0 through 9. And then each one of these is a 28 by 28 pixel image, where each pixel in and of itself is an 8-bit grayscale value. So yeah, falls within 0 to 255. So yeah, if we zoom in on this picture, it's going to be 28 on one side and 28 on the other. And then every single one of these pixels falls within the range of 0 to 255. So this means that we have 784 pixels total, and each one of those pixels is a distinct feature. So there's this data set has 784 features, or it's yeah, the D is 784. And so the task on MNIST is to learn a model to be able to classify these images based on the correct digit class. So in this case, there would be 10 classes, and we want to learn a classifier that would recognize each image as an instance of one of those classes. So we would want a classifier that would label this as 3, this as 5, and this as 8. And so clearly this is really easy for us to do as humans. Yeah, our visual system occupies a large fraction of our brains, and it evolved over hundreds of millions of years. So it's really optimized for these types of visual recognition tasks, these types of pattern recognition tasks. This is not very easy for machines to do. And it's with the philosophy of the course so far, where we've been working with the features of the original input data, or hand designing features that would allow the problem to be easier, or at least solvable, it's really not clear what feature map we could possibly design to be able to tell these classes apart. And yeah, like what set of features would actually allow us to solve the problem? It's not clear a priori how to go about that. And so this problem where we don't know what the feature should be a priori, or we don't want to make a guess. This is the motivation behind neural networks. And so, yeah, whereas previously we had been specifying or hand designing a feature map, we're now going to allow the features themselves to be learned as well. And we're going to do that while we're learning the task. And so the idea is that this is going to allow us to discover patterns on the basis of which we can make accurate predictions, even on new examples drawn from the same underlying population. And so, yeah, the idea is that everything that goes on inside this box here, that is our feature map. And so the outputs of this box, that's going to be a new set of features. So we'll from still map from some space of dimensionality D to some space M. But now we're going to each of these new features, we're going to call them hidden units. They're going to receive a weighted combination of each of the input features. So so if we're considering this hidden unit HO, that's going to receive information about each of the input features. So it's going to receive information from X1, from X2, from XD, potential, and also a bias term. But these weights themselves, we're going to let them be trainable parameters. And so we're going to, that the hidden units are going to represent a new feature space from which we can learn a linear weighting for our classifier. And then once we've gotten that far, to figure out a feature mapping or to learn a feature mapping based on the input, we're also going to generalize this to chain these layers together, or this layer of the feature mapping together, to be able to learn features of our original features, and allow successively intermediate layers of weights to be trainable as well. And so so this will be called deep neural networks, and they're very, very general. And they're applied to several different types of prediction problems, everything from computer vision, natural language processing, time series data, recommender systems. They're applied in a broad number of domains because they don't require us to hand design these features for which you would have this kind of domain knowledge. And so they're very general tools in our toolbox. And so today we're going to be thinking about or talking about three key questions. The first is that we have to get a bit more specific on what is a useful feature. So I said that it allows us to learn very general features. This is true, but there are certain restrictions that we need to take into account. So not every feature is going to give us the computational power that we need. Okay, and then after we talk about that, we're then going to get into how we estimate the parameters of our network. So what the parameters are, and then how we go about training the neural network. And through that process, we're going to learn that overfitting is a bit of a greater risk for these types of models. And so we're going to close out the lecture by thinking about how we can prevent the overfitting problem. Right. So yeah, what do we mean by useful features? Okay. So I said that our model is going to involve is going to look like this, and what we're going to be doing is taking the input features and then allowing them to interact with a set of hidden units through a set of connection weights. So that's what I said. And so and then the output of those hidden units, that'll be our new set of features phi of x. And so one way one way to think about what we might do then is to just learn a feature map that is an inner product between the original set of features X, and then some projection matrix V. So in this case, yeah, if we wanted to map from some space D to some space M, where M is the number of hidden units. Yeah, our original data that would be in art of D. One way to do that would be to design a projection matrix that is of shape D to the M. What V would look like is it would have D rows and M columns, and that would allow us to map from the space of R to the D and R to the M. And then each element in V, that would simply be a real number. Okay, so yeah, let's play this out and see what happens. So our feature space is going to be the inner product between our input vector, which is of R to the D, and then our projection matrix, which is of shape D times M, or D by M. To generate these new set of features, we need only transpose our feature vector, and then multiply that by V. Okay, so we'll go and do that out. So the first row of our feature space, it's gonna, okay, so yeah, x1 times v11 plus x2 times v21 plus xd times vd1. So that's going to give us our first row. And then for the second row, that's going to be x1 times v12, gives us that guy there. x2 times v22, give us this guy. And then finally, xd and vd2 is going to give us that there. And so we can go through all columns, multiply our feature vector by each column, and that's going to give us a column vector of shape m by 1, and then I've transpose this for just for saving space, and so then we can recognize each of our respective new features, which we now have M. So we now have M features. That's simply the sum of I through D of VI1 XI. Right. So so every one of our original input features contributes to our new feature. And then it's a linear weighting of those input features. And so yeah, if that's the case, then our classifier, or the linear predictor, so at this point here, just before we apply the sign function, that's going to be a linear combination of that new set of features, phi sub j. And so yeah, we're interested in that weighted combination of those feature vectors. So we'll be summing up, yeah, doing a linear, doing a weighted combination of those feature vectors. But we can substitute in the expression for each of our features before, which is going to be I to the 1 to d v bij xi, and that's but then we can see that wj doesn't depend on what's going on in here, and so we can take wj inside of this sum, and now we can see that we could define a new scalar ui that would be a linear combination of the input weights and the output weights wj. And so in this case, the output y hat, that would simply be a linear combination of our original input features xi given a new expression for UI. And so uh, yeah, the key takeaway here is that if our new features are simply a linear combination of our original features, that is, we just generated these new features with a simple projection matrix from the original, then it's going to collapse to being simply a linear combination of the original input features. So we haven't actually gained any expressive power. This In the case where we're simply using a projection matrix, this is no more interesting to us, no more useful to us than if we had simply allowed the network to learn a linear combination of the input weights. So this isn't what we want. So what we're going to do instead is we're going to define our features as by applying some nonlinearity. So we're going to introduce some function f, which is a nonlinear function, um, which is a nonlinear function of the weighted combination of a weighted combination of the input features. So we'll use a projection matrix to generate the new features, but then we'll apply a nonlinearity as well. And so this will give us a set of m basis functions or a set of m features, but they're going to be a nonlinear function of the weighted combination of input features. So some commonly used nonlinearities are the sigmoidal function, which is typically referred to as sigma. And so if t is the pre-activation, that would be what's going on inside these curved brackets here. And so yeah, if t is that pre-activation, is the weighted combination of original input features, then the sigmoidal function is 1 over 1 plus e to the minus t. We saw this in linear regression as well as in feature maps. It's going to give us this something like this green curve here. So it goes to 0 for very large negative numbers of pre-activations, and then goes to 1 for very large positive pre-activations, and then is 0.5 when the pre-activation is close to 0. So that's a common one. It's what people worked with when they started with multi-layer perceptrons and deep networks. Another one is the tanh function. This is a bit more common in recurrent neural networks that we'll get into soon. And then finally the rectified linear unit, which simply takes the max of 0 or the pre-activation. So in this case, if the pre-activation is less than 0, it's just going to output 0. Or if it's greater than 0, it's going to output the pre-activation. Small point of confusion on this graph, the pre-activation is called z, whereas in everything here, we're talking about it as t. One generalization of the rectified linear unit or the ReLU is we add a bias. And so in that case, B is a trainable parameter. And so we might not, whereas typically the nonlinear activation function, as we call it, is specified, or it's a hyperparameter that is chosen. In this case, if you have a trainable parameter as part of your activation, then you might not necessarily know what that nonlinear function is completely when you set up your function, when you set up your model. And so, yeah, so I said that's what we're going to be doing. Do we have any assurances about whether this is sufficient to be able to learn the types of feature maps that we um, that we might be interested in. And so it turns out that this model that we just talked about, where we're taking taking the input features of, and doing a projection into a set of hidden units, and then applying some nonlinearity, and then simply doing learning a weighted combination of those to get our outputs. It turns out that this architecture that we call a feed-forward network, um, with at least one with a linear output layer and at least one hidden layer. It turns out that that's sufficient to approximate any continuous function that maps from our input space of R to the D to some other space R to the K, where K is the dimensionality of the output, on a closed and bounded subspace of RD. And yeah, so it turns out that if we have those ingredients, we can approximate any continuous function with arbitrary degree of precision, provided that the number of units in our hidden layer is sufficient. So we call that the width of the hidden layer, and that the hidden layer has a nonlinear activation function, nonlinear and continuous. And so this is the universal approximation theorem of multilayer perceptrons. And so it guarantees that we can approximate any continuous function on a closed and bounded subspace of R to the D, provided we have enough units in our hidden layer, and each hidden unit has a nonlinear continuous activation function. Yeah, so some other comments on this. The ReLU rectified linear activation function, that is a continuous function. There's no gaps or no jumps in the output. It's not differentiable right at the point, right at that 0 point, but it's still a continuous function. And so that simple nonlinearity is enough to satisfy the conditions of this universal approximation theorem. But yeah, in order to in order to approximate the function to arbitrary precision, we might need a lot of units in this hidden layer. But we can still be guaranteed to achieve that precision if we have enough units. And so yeah, once we given those assurances of the universal approximation theorem, in general with deep neural networks, we might go deeper or add extra hidden layers. So we might have more than one hidden layer to be able to learn features of the original input features, and then to learn features of those features, and so on and so forth. And so we'll have a projection matrix from one vector space to the next, and then another projection matrix from between the intermediate hidden layers, and then on the output, in general, we might also not restrict ourselves to linear functions of the most recent hidden layer. So we might also apply some nonlinear function. So for example, we might apply a softmax function across this layer to be able to learn a classifier. We might be interested in an affine combination of activities in this in this hidden layer to have some bias associated with it. And we might also learn multiple functions at the same time um, by applying a different set of functions, a different set of functions, and getting multiple outputs. So yeah, in general, our the multi-layer perceptron or these deep networks can have an architecture like this where we've got an input, set of input features, set up maybe several hidden layers, each with their own nonlinear activation functions, and then our output layer, which may involve a set of functions, a set of functions of the original input, a set of functions of the most recent hidden layer activations. Right, and then a few more comments. I said all of that. And so yeah, the depth, we're going to refer to the depth of this network as the number of hidden layers. So in this case, we'd have two hidden layers, and then the width of each hidden layer is going to be the number of hidden units in that layer. Yeah, and then typically on the output layer, both the weights and the bias might be learnable, yeah, to be able to give us an affine function, and we could we might be interested in nonlinear functions of the hidden activations. So for example, this F might be a sigmoid for classification. We might apply a softmax if we've got a multi-class classification problem. And in some cases, you might want to learn multiple functions at once. Okay, so that was a discussion of what counts as a useful feature, and yeah, critically, we can't just learn a projection matrix from the input space to the hidden layer. We need a nonlinearity in there in order to learn useful features. But now we'll get into how do we actually learn what the parameters are? How do we fit the parameters? And so in general, as with any problem, we're interested in minimizing some loss function or minimizing the expectation of some loss function between our input data and our output or response. So given some training data sets, some examples, we want to minimize the expectation of some loss function. And so we want to find the parameters theta that minimize the expectation of the loss. And so in this, so why don't you take a minute right now to pause the video and see if you could calculate how many parameters would be in this hidden layer. Okay. So hopefully you've paused the video and done a quick calculation on your notes. Let's now go through to figure out how many parameters are in this layer. Okay, so right, the input to the hidden layer, that's our projection matrix. So we've got four features on the inputs and four features on the input, and we're going to 5 hidden units. So there's 20 parameters here. And then on the hidden layer, I've assumed a ReLU, a rectified linear unit. So I've got one. So each of those is going to have one bias per hidden unit or per neuron. So that brings us up to 25. And then on the output, let's assume an affine combination or an affine function on the output. So that's going to give us an extra five weights and one bias. So that'll be an extra 6 parameters. Then we've got 25 weights, 5 biases is or sorry, 20 weights, 5 biases is 25 parameters, plus another 5 weights and one bias. That's going to bring us up to 31 parameters. Okay, so we've got 31 parameters to fit for this multi-layer perceptron. Okay, so how do we fit these parameters? So it'd be really nice if there were a closed form expressions, if there were a closed form expression like we had in linear regression, where we could solve for the weights in one step. And so Yoshua Bengio, who is a significant figure in the deep learning community, actually explored this question with the simplest possible network setup in a workshop at NeurIPS 2015. And so in his talk, he had a network with just one input X and one hidden layer Z, and then an output Y. So there's just one input feature, one neuron in the hidden layer, and then a single output. And so the objective for this little neural network is to learn the identity function. So simply to map the input to the output directly. So yeah, if we feed it a 1, then it should output a 1. And so yeah, mathematically we can describe this network's operation with the equation y w1 times w1 times x. So the weight between x and z, that's w1, and then the weight between z and y is w2. And so in that case, y is w1, w2x. And yeah, so w1 and w2 are the weights that we're trying to learn. And so yeah, we could take the loss function as the squared error between the predicted output and the target. And so here we'd be minimizing 1 minus w1 w2 squared. And so our goal is to adjust w1 and w2 so that their product equals 1. So the network, which in this case would mean that the network's output would match the target output exactly. And so if we try to solve for w1 and w2, right, so yeah, the way to minimize this loss function is just to set w1, w2 to 1. And so, yeah, what's interesting is that if we try to solve for these weights, we can find that there's actually infinitely many solutions that satisfy this identity function requirement. So if w1 and w2 equals 1, then as long as one weight is the reciprocal of the other, we're going to minimize this loss perfectly. And so this relationship is actually going to describe a hyperbolic curve in the w1 w2 parameter space. So instead of having a single unique solution, we're going to have a whole set of solutions lying along this parabola, or lying along a hyperbola. And so this is not a convex optimization problem where we could count on just a single global minimum. And so, yeah, whereas in linear regression, we're working with a linear set of input features, and we had a convex objective. Even this hyper simple the simplest possible network we could imagine is not a convex optimization. So yeah, this example highlights the fundamental challenge in training neural networks is that even for such a simple task, the optimization landscape isn't convex. There's no single solution that the optimizer can actually, fall into. And that's was just two parameters. Yeah, so that was the simplest possible network we could imagine. But what loss function surface might we expect to see for a larger, more complex network? And so in deep learning, as we scale up to networks with thousands or millions of parameters, the optimization landscape is non-convex and is going to be extremely non-convex. So if we were capable of visualizing the loss landscape, we might see a complex pattern of peaks and valleys, some flatter regions. And so this figure that gives us a glimpse of what that surface might look like in a hypothetical deep network. And so each valley is going to each valley is going to represent a local minimum in the loss function. Um, yeah, so we can see that there's multiple minima in this hypothetical loss landscape. But what's interesting is that research indicates that most of these local minima are actually quite close to the global minimum in terms of error. And so, yeah, what this means is that even though the loss surface is full of these ups and downs, many of the valleys here end up being good enough for our purposes. And so gradient descent is therefore a reasonable approach because even if our optimizer lands in a local minimum instead of a global one, the model's performance won't be too different from if it had actually found the global one. And so it's as if the error landscape might have multiple safe zones where we can end up and still achieve a reasonably low error, which is pretty convenient given the complexity of some of the models we're going to be working with. And so, yeah, what I'm trying to convey is that this is the reason why training deep neural networks is feasible despite the rugged, complicated loss landscape. And so when we optimize these models, it's probably not going to reach the absolute lowest point or the global minimum as we could find in the convex optimization. It's still going to find a reasonably low error solution among one of the local minimum. And so, yeah, even each of those critical points, even though they're technically suboptimal, it's going to yield an error close to that at the global minimum. So that's our approach. Okay, so yeah, we're going to be using gradient descent in order to initialize start off with an initial set of parameters and then follow use gradient descent to find a local minimum. But how can we compute the gradient? How can we compute the gradient of the loss for a multi-layer perceptron? Okay, so let's start off with a simple example. So we'll get rid of the hidden layers in our neural network, and we'll just focus on the case where we're trying to, or we have a network where we've got input features, and then our output is simply a linear weighting of those input features, or more specifically, an affine function of those input features. So we've got three parameters: W1, W2 and then a bias. So let's select squared loss as our loss function. So if the output of the network is y hat, then we're simply comparing that to the true label y, and then we're going to square that and divide it by two, where the half is for mathematical convenience later. And so in this network, the output of the network is just z. So the everything coming into this node, so w1x1, yeah, and then sorry, so z in turn is then w1x1, w2x2, and plus b out. So the output, our prediction is simply an affine combination, affine function of the original input features. That's the structure of the network. Okay, and what we want to do is figure out the gradient of the loss with respect to the parameters, and we'll just focus on one parameter for now. And so what we can see, so that would be partial L over partial W1. And in order to compute that, we're going to have to apply the chain rule. So that would be the partial derivative of the loss with respect to the network prediction, and then the prediction with respect to what's going on in the node Z, and then Z with respect to the actual parameter. And if we multiply those together, then we'll be able to compute the gradient of the loss with respect to W1. And so the gradient of the loss with respect to the prediction with respect to y hat, that's and we just need to take the derivative of half y hat y squared, so that then the two would come down, cancel out the half. We'd be left with y hat minus y. But then we also need to apply the chain rule for what's going on in there. And so the derivative of y hat minus y is just one. So this leaves us with simply the prediction error as the gradient of the loss with respect to y hat. And now the gradient of y hat, or the partial derivative of y hat with respect to z, that's d by dz of simply z now, because y hat is equal to z. And so that's just going to be one in this case. And then last but not least, the partial derivative of z with respect to w1. Now that's d by dw1 of this function here. And so now we can see that from the perspective of w1, these two terms are just constants. And so the only thing that w1 cares about is the value of input feature x1. So that would simply be x1. And so then we can combine or multiply all those together. So to get the partial derivative of the loss with respect to w1. And so that would be y hat minus y, and then 1 for partial y hat by partial of z, and then partial derivative of z with respect to w1 would simply be x. And so this would give us the gradient of L with respect to W1. And so in a gradient descent algorithm, we would just move in the direction opposite of this, or take a small step in the opposite direction of this. And so one way to think about this is that if the error were large, or if we had some large error, and we were and that feature was also giving us a large value, at that same time we would want to decrease the weight onto that vector, or onto that input feature. All right, and yeah, and then we could substitute back in our expression for y hat and z, and get something like that. Let's now consider a slightly more complicated example where the output is a nonlinear function of z, as is more generally the case in these neural networks. So we'll still use the squared loss, but now y hat is some function f of z, and we'll be agnostic about what exactly that is, but what exactly f is. But then z is still going to be the current flowing into that pink node. And so yeah, z itself will be still w1x1 plus w2x2 plus that b out, where's the bias. And so as before, we're still going to use the chain rule. The partial derivative of the loss with respect to y hat, that's not going to change in this case. But now the partial derivative of y hat with respect to z, that's going to be different. Because y hat is not equal to z anymore, and so the gradient is not simply 1. Instead, we want to be doing d by dz of f of z. And so because we've been agnostic about what f is, in general, this is going to be the first derivative of f evaluated at z. And then dz by dw1, that's not going to change. That's still going to be x1. And so bringing this all together, then we'll have the partial derivative of the loss with respect to w1. That's still going to be applying the chain rule and multiplying those all together. Okay, so let's now consider the case that we're actually interested in, where we've got a slightly more complicated network. We've got a multi-layer perceptron where we have a set of input features being projected to a hidden layer through some intermediate set of weights, W1 and W2, and to which we're applying a bias to get our activations that we'll call A. And these activations A, those are going to be the outputs of this hidden node using a nonlinear function that I'll get to in a second. And then once we have the output of that node, we're going to scale that by some amount W out, add a bias, and then pass that through another function F to get our final output. So the output of this whole network, the prediction of this network is y hat is going to be f of z, where z is the total current flowing into this pink node. Okay, so working backwards, yeah, z is going to be w out a plus b out, so the total current flowing into this pink node. To get the activations A, to get the output of this purple node here, we're going to apply some other function h to t, and then t in turn is going to be the total current flowing into this purple node. So that's going to be w1x1 plus w2x2. Get that there, and then the bias into this hidden node there. So this is our model for the multi-layer perceptron. Now, let's still focus on the subproblem of computing the gradient of the loss with respect to one single parameter W1. And so we're still going to be working with the chain rule. So as before, this will be partial derivative of L with respect to y hat, and then partial derivative of y hat with respect to z. And then, but now we need to do the partial derivative of z with respect to a, and then a with respect to t, and then t with respect to finally w1. And so we know how to compute the partial derivative of L with respect to y hat, and then y hat with respect to z. So we don't need to go through those again. But the partial derivative of z with respect to a, that's going to be d by dA of w out a plus b out, so taking this function here. And then from the perspective of a, the bias is a constant, and so it's only going to care about the final output weight. Okay. And then bringing that back, the partial derivative of A with respect to T, so getting this fourth term of the chain rule, d by d, now we want to do d by dt of h of t. So we're dA by dt, we're just substituting in this expression here. But because we haven't specified what this function h actually is, we just needed to, we're interested in the first derivative of h with respect to t. And then the partial derivative of t with respect to w1, we want to look at this expression here. And so d by dw1 of that whole expression, again, those terms are constant, and so the only factor that w1 cares about is x1. And so putting all of that together, we're going to have the prediction error as before, the first derivative of z that we calculated in the last slide, and now partial z by partial a, that's going to give us, put in w out, partial a by partial t, that's going to give us h prime of t, and then x1 as before. And so what we've done is we've propagated, we started at this final layer. We've done successive partial derivatives with respect to the parameters and activation functions at previous layers. And so that in order to compute the gradient of the loss with respect to a parameter that occurs in the shallowest layers of the network, we need to know the gradient of the loss at everything that came after it. And so the chain rule is as we just applied it, is fundamental to computing the gradients for training a deep network. And it turns out that the activation function that we select has a big effect on our ability to train a network using gradient information. And so a major issue that can arise in computing these gradients is something called the vanishing gradient problem. And so essentially, as we propagate those gradients back through many layers, they're going to get smaller and smaller because we're multiplying these gradients together. So if you have, if for example, this is a small number and that's a small number, then together they're going to give you an even smaller number. So that's the idea between this vanishing gradient problem is if you have a lot of layers in your network, you're going to get the gradients might have a tendency to vanish as you try to propagate them backwards. The sigmoid function, for example, which maps its inputs or its pre-activations between 0 and 1, it's got a very you can see that it's got a very shallow slope for large negative numbers or for large positive numbers, and so what that means is that this shallow slope is going to correspond to a small gradient value. And so it'll do okay here where it's got a steep slope, but for larger pre-activations, when we've got larger pre-activations, the gradients are going to be small. And so, the takeaway is that sigmoid activations in very deep networks, the gradients could diminish significantly as they move backwards through each layer. And so the ReLU, or the rectified linear function, rectified linear unit, on the other hand, is going to behave totally differently. And so the ReLU function is going to output 0 for negative input, but it's going to have a slope of 1 for positive inputs. And so this linear slope for positive values of z means that ReLU is going to avoid the problem of vanishing gradients entirely for a large range of possible inputs. And so as long as the neuron is active, the gradient is going to remain constant during backpropagation. And so this is going to allow it to propagate effectively through many layers without diminishing. And so this property has made the ReLU and some of its variants, the default activation functions, default activation function in most deep networks today. It really is the workhorse in multi-layer perceptrons. Surprisingly, whereas the field of deep learning started off using sigmoid, the sigmoid activation function, the ReLU actually arose much later and really only discovered in 2011 or 2012. Okay, so we've talked about what we mean by useful features. We also went over how to apply the chain rule to learning the parameters of these networks. And what we discovered was that there are quite a few parameters in this network. So for a simple data set where we had four input features, our model had 31 parameters. And as we saw before, this is relatively complex. And this is a relatively complex model. And so one thing we need to think about is the risk of overfitting. Yeah, let's talk about that a little bit more. So yeah, why am I making this claim that neural networks are susceptible to overfitting? And so it all comes down to this balance between complexity and generalization. So yeah, many times throughout the course thus far, we saw that as we increased the model's complexity, which we can think of as, its flexibility or the number of patterns it can capture, the training error reliably tends to decrease. And so yeah, and this blue curve here that shows the training error consistently dropping as we increase the model complexity, sometimes called the degrees of freedom. Is because a more complex model can fit the training data more closely. It can capture, really like tiny details. But the test error has a different pattern. And so most often, as we increase model complexity, initially we'll see an improvement on the test error. Our model is learning useful patterns that allow it to generalize beyond the training data set. But then as we continue to increase complexity, there's a point at which test error actually begins to rise, and that's where overfitting kicks in. So the model is now so flexible that it's not just capturing, useful patterns, but it's also capturing noise and peculiarities that are specific to the given training data set. And so as a result, it's performing worse on new unseen data. And yeah, previously, like in the ensemble methods lecture, we called this phenomenon a high variance situation. And so, whereas before, if we had a model with P parameters, N training samples, and D features, the models that we have tended to be building, the number of parameters was on the order of the number of dimensions. So the perceptron algorithm, for example, that the number of parameters in that network was equal to the number of features plus one for the bias. And we typically, in either of these cases, that the number of parameters was much less than the number of training data we had. So we always had way more, we could normally count on way more training data than the number of parameters. In neural networks, on the other hand, the number of parameters that we're dealing with tends to be greater than the product of the number of training examples and the dimensionality of the data set. Yeah, so P is P is often far greater than the product of the features in the samples. And often what this means is that models have more than enough capacity to actually just straight out memorize the training data exactly if we allow them to. So they have enormous representational power that gives neural networks the flexibility to fit almost anything. But this is a double-edged sword because it increases the risk of overfitting. Um, this is so to drive home this point, this is a plot of the model parameters in billions over time as a function of year. Um, so the number of parameters in large language models over the years. And so in back in 2018, before we had large language models, really, we were dealing with parameters, dealing with networks that were relatively small, so maybe 500 million parameters, something like that. You might remember GPT-3, which kind of broke the internet when it came out sometime during the pandemic. So that had 175 billion parameters. Just sitting just below this 200 billion parameter mark here. So that was in can't remember exactly when that was, maybe December of 2020. And then since then, uh, it's grown even more, right? So GPT-4 is about 1.7 trillion parameters. Um, so they have enormous representational capacity. And so uh, we need to be able to manage this risk of overfitting. Um, to be able to not just fit the training data set, but also generalize to new unseen data. What techniques do we have to impose some kind of regularization on these deep networks? So when training large models with sufficient representational capacity to overfit the task, when we're applying gradient descent to train these models iteratively, one thing that we notice is that the training set loss is going to decrease regularly or decrease consistently over time. So this is a plot of the number of epochs or the number of gradient updates that we've performed, and this is the loss, the loss on this side. So we've got training set loss and then validation set loss. So that the training error is going to decrease consistently. But if we were to regularly check in with how it's doing on a corresponding validation set, then we would see an initial drop. But then at some point, it's going to stop improving and may actually get worse if training were to continue. And so this noticing this has motivated a technique called early stopping. And so what we do here is we just as we set aside a separate validation set, and then periodically evaluate the model on that validation set. And then we're going to save a copy of the model only every time the error on the validation set improves. And then when the training algorithm terminates, we're just going to return to that last save copy. This is actually just a good idea in practice, a good idea in general, because if these models tend to be very large, then you don't want something like a power loss in your building, or your laptop turning off, or Windows deciding that's the best time to update your computer. You don't want that to destroy all the work you've done so far. And so checkpointing of checkpointing is a good practice to provide a partially to save a partially trained model as you go. And so there's a couple. This early stopping is built into a wide range of libraries. It's typically something that you can use just off the shelf. A lot of libraries include this hyperparameter called patience, which allows you, it just that, yeah, corresponds to the number of times to observe worsening validation set error before giving up. Yeah, if you, then you wouldn't have to, keep training the model over all of these epochs where what you're really interested in is just its performance right around here. And so you might get to this point and then stop training and call it a day. Um, yeah, interestingly, you can think of early stopping as kind of trying to find the number of time steps that is optimal for your model. So it's almost like a hyperparameter, uh, except one where you only need a single run of training to figure out what the number of time steps should be. Another technique is called weight decay. And so this actually falls out of ridge regression. And so if you recall, the ridge regression objective, we specify a loss function where we've got our error, but then we apply a penalty, which is the penalty corresponding to the norm of the weights. And then we have this lambda hyperparameter that controls the strength of this penalty. And if we apply this when we apply this in a gradient descent scenario, which isn't something we've done before, then the gradient of this loss function is going to be equal to lambda w, so that 2 comes down, cancels out the half, and we're left with lambda w, and then the expectation of the gradient of the loss on that side. And then we're going to be taking a step in the direction opposite of this gradient. So if this is our gradient, then we'll be taking a step of size eta in the direction opposite of this gradient. So that's the gradient of the loss there with respect to the weights. And then our new weights, the new weights are going to be the weights at the previous time step less some fraction of the gradient. But it turns out that this expression here can be rewritten like this, and so we can think about it as taking a step in the direction opposite of the gradient, but then also scaling the last weights down by some amount 1 minus eta lambda. So yeah, eta is usually small. So this term here is going to have the effect of decreasing the size of the weights over time, and so that's why we call it weight decay. Another way to make the machine learning model generalize better is to train it on more data. And so in practice, the amount of data we have is limited. But one way to get around this problem is to create essentially fake data and add it to the training data set. And so for some machine learning tasks, it's relatively straightforward to generate new fake data. And so, the idea here is that, for example, an image classification task, potentially we're given one image. I realized that this image would almost certainly have to have been AI generated because this cat's fingers don't look real. But yeah, we start with original image, and then we can apply some transformations to it, some transformations that are meaningful for this type of data set. So in images, we want maybe this would be horizontal, or flipping it along vertical. Might apply some rotations, a blurring operation to make it brighter or add noise, take out color altogether, or apply a cropping feature. Um, and so what we've expanded or augmented the original data set by applying these transformations. And what we're telling the classifier when we say this is, I want you to be invariant to these types of transformations. I want you to recognize that this is a cat, regardless of if it's flipped upside down or rotated slightly or blurred. You need to still recognize that that is a cat. And so we can see now that there are certain, we might imagine other types of data sets where you need to be a little bit careful in terms of how you augment the data or how you do data augmentation. So for example, in optical characterization, optical character recognition tasks, you can't just do a 180-degree rotation on a 6 because that's going to give you a 9, and that would actually change what the correct class is. Similarly, you can't flip a B about the vertical line or about the vertical axis because that's going to give you D, again, changing what the correct class is. There's certain types, certain tasks for which data augmentation is even it's even less clear how to do data augmentation correctly. For example, if for a task like density estimation, where you don't even know the distribution of the data that you're working with, it's unclear how to apply data augmentation. Because you don't even know, you really need to know something about the distribution in order to augment it appropriately. And so, yeah, data augmentation enjoys widespread use in these image classification tasks, or these object recognition tasks. And so it's a very, very common technique if that's the task that you're working on, because it's clear what types of transformations wouldn't change the correct class. A really popular technique for regularizing deep networks is something called dropout. And so dropout is a technique in neural networks that helps prevent certain parts of the network from becoming overly important by kind of randomly dropping out nodes during training. And so, yeah, in dropout, each node is dropped out with a certain probability p, and then retained with a probability of 1 minus p. And so the dropout process is applied independently for each training point, and the idea is that this is going to create a unique sub network for every single training point. And then during gradient computation, only the parameters associated with the retained subnetwork are updated for that training point. So for example, in a neural network with a dropout probability of 0.5, each node would be dropped half the time during training, and then while the other half would be kept with their connections intact. And so this approach effectively, or the idea is that this prevents overfitting by discouraging dependency on specific nodes, and encourages a more generalized representation across the network. So in math, the activation function h essentially becomes a random variable, and so p% of the time, the activation function is 0. So this corresponds to the case where we're dropping out a node. And then because dropping nodes decreases the input to the nodes in the next layer, that's going to lead to a scaling issue. And so to resolve this, we essentially apply inverted dropout by scaling the active nodes outputs by a factor of 1 minus p. And so the reason why this works is because the expectation of the activation remains unchanged. And then finally, at test time, we don't do dropout at all. The full network is used without any nodes being dropped to ensure stable predictions. Uh, yeah, and so if this were a multi-layer network, you could actually apply P to different dropout probabilities to different layers. Um, so yeah, this is a favored approach in the field. It's got several advantages. Um, it's computationally cheap. So using dropout requires only generating uh, O to the uh, n binary numbers and then multiplying them by the state. So that's going to scale as linearly in n for each computation per sample per update. Again, we're applying dropout to each sample independently. And then at inference time, we don't do dropout at all. So it doesn't cost us anything there to apply this regularization technique. Like I said, it's also got some flexibility because you can apply different probabilities to different layers, which might be desirable for certain types of tasks. And it's also compatible with most architectures and and training procedures. So it's a very general regularization technique. Yeah, and yeah, because it's so advantageous, you can find it in most deep learning libraries. And apparently, the Srivastasa, he has shown an improvement over weight decay, an improvement of dropout over weight decay. One last trick that has the effect of alleviating overfitting concerns a data preprocessing step called normalization. And so the main goal of normalization is to get all features on a consistent scale, typically with a mean of 0 and a variance of 1. And so this might sound like a minor tweak, but it's actually a really powerful tool for speeding up the learning process. So the idea is that by making sure that features are on the same scale, normalization is going to help our model navigate the loss landscape more smoothly. And it does provide a little bit of regularization, which I'll explain in just a moment. So yeah, to understand why normalization speeds up the learning process, we can think about how gradient descent works. And so the job of gradient descent is to find the minimum of the loss function by taking steps in the direction of steepest descent. But if each feature in our model has a different scale, the shape of the loss landscape can become skewed. And so we could imagine a narrow valley, or kind of a steep ravine on either side. And so this uneven shape is what's called an ill-conditioned landscape, and this makes it challenging for gradient descent to find a smooth path to the minimum. And so the idea is that if one feature has a much larger scale than another, the gradients for that feature are also going to be larger. And so as gradient descent updates the weights, it's going to take big steps in the direction of the feature that's changing more quickly, and then small steps in the direction that's changing more slowly. So we're gonna moving quickly in this direction, and not so much in this direction. And it's going to cause the optimization path to zigzag, and which is going to slow down the journey towards the ultimate minimum in the green here. And so, yeah, it's going to be especially problematic in deep networks where these updates are going to ripple back through multiple layers. And so it's as if the optimizer has to constantly correct its course, and this makes training inefficient. And so normalization helps by reshaping this loss landscape to be more circular, or at least less stretched out. And so when all features are on this consistent scale, the gradient updates become more balanced across directions. And so this will allow the optimizer to make smoother, more direct progress towards the minimum. And so this smoothing out affects, helps prevent the zigzagging and lets the optimizer take larger, more confident steps without overshooting on its path towards a solution. Um, and because this, as a byproduct, it introduces a bit of randomness in the batches. So normalization is going to act as a light form of regularization, making it less likely for the model to overfit to specific patterns in the training data. So in terms of how batch normalization works in deep learning, we can start with the simpler situation of normalizing the input features. And so at its core, batch normalization aims to make the training process smoother by ensuring that each mini batch of data has a consistent distribution. And so for each mini batch, we're going to calculate the mean, denoted as mu sub b, and the variance, sigma b squared, for the activations. And so the idea is that this step is going to center and scale the data to have zero mean and unit variance, to help stabilize the training. And then we're also going to add to the variance calculation a tiny constant, epsilon. And this is to prevent division by zero in the case where we happen to compute a zero variance across a mini batch. So this ensures that the process is going to remain stable even with small variance values. And so after normalization, we introduce two learnable parameters, gamma and beta. And so gamma allows the network to stretch these normalized values, and beta shifts them to new locations. So this adaptability allows the network to go beyond the standard zero mean unit variance distributions, and to help improve its performance on specific tasks. And then, when it comes to, and then during inference, instead of calculating the mean and variance for each mini batch, batch normalization uses the gamma and beta values to scale and shift the inputs accordingly. And as I said, normalization can act as a kind of regularization. By normalizing each mini batch independently, we're kind of introducing slight variations or noise into the activations across batches. And that helps prevent the model from memorizing specific patterns, and can reduce overfitting a little bit, similar to how dropout works. But it's essential to use batch normalization in conjunction with other regularization techniques like dropout or weight decay, especially in complex models. It's worth noting that batch normalization also requires a reasonable batch size to produce reliable statistics. Small batches can lead to really noisy estimates, which might destabilize the model completely. So in terms of benefits, allows us to improve optimization by creating that consistent scale across features. Talked about how it's providing a little bit of regularization. We do need that reasonable batch size, like I said. We do need some assurances that the distribution shouldn't vary significantly between batches. And so for most of the tasks that we've encountered in this course, where we've been getting a single block of data as a training data set, and we've been making this assumption that the individual batches are drawn or constructed IID from that training data set. There are other tasks like reinforcement learning where that's not the case. So in RL, for example, the agent is is moving around an environment or navigating an observation space in some way. And so we would expect batches or the distribution observed in a given batch to vary significantly from one to the next. And so, yeah, batch normalization doesn't make sense in a reinforcement learning context. Yeah, and as I said, it should be used in combination with other techniques. In practice, um, in deep learning, for each mini batch of data, we calculate the mean and variance of the pre-activation values for each neuron. So the statistics allow to normalize each neuron's input to a zero mean and unit variance across the batch. And then once normalized, the gamma and beta parameters allow us to fine tune the scale and shift of these pre-activations. And then batch normalization can instead be applied to entire layers instead of individual neurons. So this is useful in scenarios where the data distributions vary significantly over time or from batch to batch. So for in these cases, we called layer normalization. We calculate the mean and variance across all neurons for each data point individually, rather than across a batch. And so this approach ensures stability in models dealing with sequences or time series where the distribution of data points can shift over time. Okay, so yeah, we're coming up on the end of this lecture, and we have spent quite a bit of time talking about how to regularize these networks, some of the hyperparameters associated with it, and so things have gotten a lot more complicated than the simpler models that we had seen so far. And so, yeah, when do we actually need to use these models? So the Introduction to Statistical Learning text has a really great discussion of this. So they had a data set involving the salaries of baseball players. So there's 263 observations or players, and each one was characterized by a set of 19 features. And what they wanted to do was select or predict the salary of a given baseball player based on 19 variables. And so they applied a standard linear regression to the problem, lasso regression, and then they also looked at a neural network solution. And so the linear regression had 20 parameters, so there was the 19 variables and then the bias. Using lasso to sparsify the model and only focus on the most important features, they got that down to 12. The neural network, on the other hand, had 1,345 parameters. Remarkably, the test error was almost exactly the same across all three models. The lasso, yeah, maybe did a smidge better, but not too much. So what this means is that even though the neural network had more parameters to work with, that doesn't necessarily translate to better performance. And yeah, even to get that result, it required quite a bit of playing around with to select what those hyperparameters should be, potentially playing with the architecture, and it didn't allow them to reap any gains in terms of accuracy. On the other hand, the parameter values themselves didn't give any insight into the problem. So for example, using one of the linear methods or lasso, you can go back and look at what those coefficients were. In those cases, and then use that to interpret the relative importance of the number of the features in determining the output or the response. So in that case, the hits had a number of hits had a high coefficient, um, followed closely by the C runs parameter. And so these linear models also provide some interpretability, whereas the neural network is really a black box and uh, doesn't really suggest it's not immediately clear what the parameters mean in terms of the relative importance of the base variables in the data set. And so yeah, the takeaway is that yeah, neural networks are a very powerful general option, but there could be simpler models that could get the job done. Um, yeah, so a good rule of thumb would be to consider simpler models first, and to move on to neural networks if those simpler models have failed, and especially if interpretability is not important, and you have a lot of data, then a neural network might be appropriate. Okay, so that brings us to the end of this lecture. So let's do a quick summary on what it is that we talked about. So yeah, we started off thinking about cases where we actually need to learn the features instead of when we can hand design them. We also talked about the universal approximation theorem of a multi-layer perceptron, specifically that it requires a hidden given a network with a single layer of hidden units that have a nonlinear activation function, then we can approximate any continuous function on a closed and bounded subset of our original domain, given that we have enough units in that hidden layer. We also went through several examples of using the chain rule to compute the gradient with respect to the parameters in our network. We also went over some theoretical issues that arise in neural networks, specifically the vanishing gradient problem, the fact that we have more complex network. And so these theoretical issues, we have to address them in order to apply multi-layer perceptrons to real data. We went over the architecture and the parameterization of a multi-layer perceptron. We spent a lot of time going over strategies to reduce overfitting, or regularization strategies for multi-layer perceptrons. Specifically, we covered early stopping, weight decay, data augmentation, dropout, as well as batch and layer normalization. And then last but not least, we went into the considerations of when you might want to apply a traditional machine learning algorithm or a neural network, depending on the nature of the problem, how much data you have, as well as your specific goals. Like, do you need an interpretable model or not? All right, well, thanks for your attention. I hope you enjoyed this lecture. We'll see you back here again next time, where we're going to start talking about convolutional neural networks.